Did you catch that recent SpaceX launch?
Yeah, the exhaust plume changed shape the higher it got.
That's due to atmospheric pressure decreasing with altitude. The exhaust expands more to low pressure environments.
That expansion can actually change thrust efficiency. That's what we're modeling in this project.
Our goal is to analyze how atmospheric pressure affects rocket exhaust expansion and thrust. We're using ANSYS to simulate the fluid behavior in a nozzle.
We use 2D converging, diverging nozzle models. It's simplified but accurate enough to observe key changes in exhaust shape and temperature with altitude.
As altitude increases, the surrounding pressure drops. That allows exhaust gases to expand more, which impacts heat distribution and thrust. To estimate how fast exhaust travels, we use the isentropic velocity equation.
This shows how velocity increases as exhaust expands and pressure drops, especially at higher altitudes.
We also use the choked flow mass rate equation to understand how much gas exits the nozzle.
These two equations help us define how flow, speed, and mass change with pressure, and how that affects thrust.
We ran simulations in ANSYS Fluent with non-slip conditions and variable ambient pressures from sea level up to high altitudes.
We use standard atmosphere models to define how pressure changes with height.
Our geometry is symmetrical, so 2D was enough to capture behavior effectively. We measured thrust changes, temperature contours, and velocity vectors.
As altitude increases, we saw greater expansion of the exhaust. The gas spread wider and cooler in the low pressure environments.
Some nozzle shapes maintain thrust better than others. Higher expansion ratios performed more efficiently at high altitudes.
The results supported what we expected. Ambient pressure has a clear impact on exhaust behavior and nozzle efficiency.
Rockets like Falcon 9 already use stage-specific nozzles, optimized for different altitudes, and our simulation reinforces why that matters.
This helped us understand the relationship between thermofluid dynamics and nozzle performance in changing atmospheric conditions.
We visualized how pressure, temperature, and flow interact and how to optimize thrust using these factors.
Hello everyone, my name is Kevin Pena, and today I will be presenting our project on rocket nozzles. So, why did we choose rocket nozzles? Being interested in technology and space and how it continues to advance, we wanted to see what areas we could investigate. For context, a rocket nozzle is a crucial component in rocket engines, responsible for converting high-pressure, high-temperature combustion products into a high-velocity exhaust gases that propel the rocket forward. Now, how do we implement this into a simulation? Our simulation consisted of a 2D asymmetrical nozzle using CFD and VISID analysis. For our goal, we're testing the effects of altering parameters on nozzle efficiency. Now, for our geometry, this is a general idea of our geometry and the parameters that were changed with several design points, which were the outlet angle and the outlet length. For our mesh, this is our general idea of our mesh. We decided to do, for the two spaces, the diverging and converging, we did phase sizings, which were 0.005 in size, and then for the middle separation, we decided to do an edge sizing, which is about 0.0025. These were our parameters for our simulation, and these are some of our ground truth calculations which we got from a textbook. This is a picture of our results using a contour plot of the Mach number, and for this specific result we are showing a 20-degree nozzle which we created, which has a 2.97 Mach speed at exit, which is showing an improving on thrust. And some takeaways from this is that we can see that the Mach number increases toward the throat and beyond in the converging and diverging nozzles. There's also a variation in the Mach number as at the exit suggests boundary layer growth, separation, or it could be due to poor nozzle design. As well as for the nozzle shape optimization, we saw that a well-optimized divergent section minimizes shock formation and boundary layer separation, and a more uniform exit velocity profile improves the kinetic energy transfer and the thrust. Thank you.